In the last class, we initiated our study of arithmetic coding. We saw that the interval in which the tag for a particular sequence resides is disjoint from all intervals in which the tag for any other sequence resides. As such, any member of this interval can be used as a tag. One popular choice is to use the lower limit of the interval. Another possibility is to use the midpoint of this interval. For our discussion, we will use the midpoint of this interval. In order to see how the tag generation procedure works mathematically, let us start with sequences of length 1. Suppose we have a source that puts out some symbols given as S1, S2 up to Sm. We map the symbols Si to real numbers I. Like in our study pertaining to Shannon-Fano-Ilias coding, we will use the same mapping, in this case to X maps the letters of this source alphabet to integers I, where Si belongs to source S. We can define a function f tilde similar to what we did in Shannon-Fano-Ilias coding, and this we could call it as a modified PDF as plus half of probability of random variable x is equal to I, and this by definition is equal to cumulative probability distribution plus half probability x is equal to I. So, for each Si, this function will have a unique value, and this value can be used as a unique tag for Si. So, this value will be used as a unique tag for Si. So, let us consider an example. Consider a source with 6 letters let us assume that this source is 0 memory IID source. We use the mapping where I is a integer. So, the outcomes of this source are mapped to the numbers 1, 2, 3, 4, 5 and 6. So, since we are assuming IID, probability of random variable x is equal to k, where k goes from 1 to 6 is equal to 1 by 6 for k equal to 1 to 6. So, if we use this equation, let us call this equation number 1. If we use this equation, then we can find out the value of that function for 2 as where I am using a simplified notation. Probability of x is equal to k is denoted by probability p suffix k, and similarly the tag for x is equal to random variable equal to 5 can be found out as 0.75. So, using this concept we can find out the tags for other outcomes also 1, 3, 4, 6, and they will be as follows. So, outcome and the tag, we have already seen the outcome for 1 and 5. So, the outcome 1, 3, 4, 6. Using that equation we can find out the tag values as given here. This means that 3, 3 keeps on recovering. This bar indicates .5833, and finally for the outcome 6 the tag value is 0.9166. Now, this approach can be easily extended to longer sequences by imposing some kind of an order on the sequences. We need an ordering on the sequences because we will assign a tag to a particular sequence. For example, let us denote the particular sequence as x with a underscore given like this. Then this denotes a sequence. Then we will generate a tag for this sequence by using some kind of ordering on the sequence as follows. Is equal to we will call this equation number 2. Here x is a sequence, m denotes the length of the sequence. This is the tag which we are generating for the sequence x. This equation is similar to what we saw in the earlier case for sequences of length 1, where I have some kind of a cumulative distribution function plus half the probability of that sequence, where y is any sequence, y sequence less than x sequence means that sequence y precedes sequence x in the ordering. Now, in order to utilize this, an easy ordering to use is what is known as lexicographic ordering. In lexicographic ordering, the ordering of letters in an alphabet induces an ordering on the words constructed from this alphabet. The ordering of words in a dictionary is a good example of lexicographic ordering. Dictionary ordering is sometimes used as a synonym for lexicographic ordering. So, let us extend the earlier example to the sequences of length 2. So, let me assume that I have two identical sources, each source consisting of 6 letters from S1 to S6, and we use the same mapping to convert the outcome to real numbers, in this specific case to be integers. Then I take two sources, identical sources, these are both IID sources, and I observe the outcome of these two sources as a concatenation of the outcomes of the individual sources. So, using the ordering scheme described earlier, the outcomes in order would be 1 1, 1 2, 1 3 up to 6 6. So, if I observe both these sources together and look at the concatenation of the outcomes, I will get this as my outcomes. Now, the tags for these outcomes can be generated using this equation number 2. For example, the tag for the sequence 1 3 will be generated as probability of sequence equal to 1 1 plus probability of sequence 1 2 plus half the probability of the sequence equal to 1 3. So, these are the sequences 1 1 and 1 2, that is nothing but y sequences which is less than the given sequence x 1 3. So, if I assume that these are IID sources, then the probability for the sequence equal to 1 1 is 1 by 36. Similarly, for this is 1 by 36, and for this is half multiplied by 1 by 36, and this turns out to be 5 by 72. So, notice that to generate the tag for 1 by 1 for the sequence 1 3, we did not have to generate a tag for every other possible message. However, we need to know the probability of every sequence that is less than the sequence for which the tag is being generated. Now, the requirement that the probability of all sequences of a given length be explicitly calculated can be as prohibitive as the requirement that we have code words for all sequences of a given length. Now, fortunately, we will see that to do so, we need only the probability of individual source or the probability model for that source. So, let us now recall that given a construction, the interval containing the tag value for a given sequence is disjoint from the intervals containing the tag values of all other sequences. This we have seen. What this implies is that any value in this interval would be a unique identifier for the sequence X. Therefore, to fulfill our initial objective of uniquely identifying each sequence, it would be sufficient to compute the upper and lower limits of the interval containing the tag and select any value in that interval. Now, we will see that the upper and the lower limits can be computed recursively, and we will try to understand this computation with the help of an example. So, let me again consider the earlier source consisting of 6 letters from S1 to S6. I use my standard mapping X Si equal to I. So, the outcomes of this source are integers from 1 to 6. What we need is to generate the tags for the sequences of different lengths. So, let us find the upper and lower limits of the interval containing the tag for the sequence 3 to 2. Let us first assume that we are observing this sequence 3 to 2 in a sequential manner. So, if we do that, then let us denote the upper limit of this interval as U superscript n, and the lower limit as L superscript n, where n denotes the length of the sequence. So, the first symbol or the integer which we observe in the sequence is 3. Therefore, let us generate the tag at the stage when we observe the symbol corresponding to 3, that is S3. So, if we follow the discussion, then U1 is given by Fx3 and L1 is given by Fx2. So, 1 denotes the length of the sequence at this stage. So, this upper limit and this is a lower limit. After we have observed 3, the next symbol to be observed in the sequence is 2. Therefore, the sequence X becomes 3, 2. Now, to generate the upper and the lower limits for this sequence, by definition, U2 is Fx2 3, 2 and L2 is Fx2 3, 1. Now, we need to calculate these quantities out here. So, let us calculate these two quantities. Fx232 is nothing but probability of sequences starting from 1, 1. So probability of sequence 1 1, 1 2 up to 1 6 plus probability of sequence 2 1 up to 2 6 plus probability of sequence 3 1, and then finally the probability of the sequence 3 2. Now if you look at any of these terms out here, these are nothing but written as this. Look at this term out here, 6 terms, and 6 terms out here. All these 6 terms can be put as one term shown here. So probability of a sequence equal to ki, where I goes from 1 to 6, is nothing but probability of x1 is equal to k and x2 is equal to I, and that is equal to probability of x1 is equal to k. So where sequence x consisting of 2 letters x1 and x2. So using this relationship, we calculate fx2 3 2 as probability of x1 is equal to 1, probability of x1 is equal to 2, and probability of sequence equal to 3 1, and probability of sequence equal to 3 2. Now this by definition is a cumulative distribution function for 2, and this we have written here. If we assume IID source, then we can calculate probability of the sequence 3 1 and 3 2 as follows. Probability of sequence 3 1 is given by probability of x1 equal to 3 and probability of x2 equal to 1, assuming these are IID, and similarly probability of sequence 3 2 is given by this relationship. So finally we can write probability of the sequence 3 1 and probability of sequence 3 2, summation of these two quantities is this, and this on simplification turns out to be probability of x1 equal to 3 and the cumulative distribution function for 2. Now it is to be noted that marginal probabilities, that is p of x1 equal to 3, is nothing but the difference of the cumulative distribution function. This by definition of the cumulative distribution function, and therefore we can write the summation of sequence probability of the sequence 3 1 and probability of sequence 3 2 as shown here. And finally, using these relationships, we can write fx2 3 2 as shown here. So this can be rewritten as, because by definition this is the upper limit for the interval corresponding to the sequence of length 2. So this quantity is replaced by the u2. fx2 is basically the lower limit of the sequence of length 1, and fx3 is the upper limit of the sequence of length 1, and again this is a lower limit, and fx2. Now similarly, based on these arguments, we can find out fx2 3 1, and it is easy to show that this expression will be obtained. Now again, this is nothing but the lower limit for the sequence of length 2, and this is again the lower limit of sequence 1. So if we substitute, we get this relationship. So at the end of observing 3 2, the upper limits for the interval where the tag for this sequence will reside are given by this and this quantity U2 and L2. Now, the next letter in the sequence to be observed is 2, and then the sequence becomes as 3, 2, 2. So, by definition we are supposed to calculate the upper limit for the tag in which the tag for this sequence, the interval for the tag for this sequence. So, that will be given by as U3, that is by definition nothing but fx3 3 2 2, and L3 is fx3 3 2 1. Now, it can be shown that fx3 2 3 2 2 is nothing but given by this expression. It is not very difficult to see the relationship between this and what we saw earlier here. If you look at this relationship, if you observe this, the first term out here is the cumulative distribution function obtained for the sequence earlier to 2, that is 3 minus 1. So, 3 minus 1 is 2. So, that is the cumulative distribution function for this. This is the cumulative distribution function for the sequence here, and again this is a cumulative distribution function for the sequence earlier to 2 but minus 1. So, based on this concept, we can see here that the sequence preceding to 2 is 3 2. So, 3 2 minus 1 is 3 1. So, this is the quantity which you will get, and out here you will get cumulative distribution function for the sequence which we obtained before 2, that is 3 2, and then again this is the same value out here. So, similarly we can obtain the lower limit for the sequence 3 2 1, and that is again given by this relationship. Now, converting this values to the limits, we get these two relationships. Now, if you observe these relationships, we can see that in general for any sequence based on this, we can write the lower limits and the upper limits as shown here. So, in general for any sequence which consists of n symbols will be given as L n is equal to the lower limit obtained in of the sequence of length n minus 1, the difference of the upper limit and the lower limit for the sequence n minus 1, and cumulative distribution function for the current symbol minus 1. So, fx xn minus 1, and then for the upper limit it is the cumulative distribution function for the symbol xn. So, if you look at this procedure, we see that there is no explicit computation of any joint probabilities, and now to generate the tag for that particular sequence, as we have said earlier, we can use the midpoint of the upper limit and the lower limit. So, if we use the midpoint of the upper limit and the lower limit, we get this relationship. So, this will form the tag for the sequence x. At this stage, sequence x consists of n symbols or n letters. So, tag for any sequence can be computed sequentially. Only information required by the tag generation is the cumulative distribution function. So, let us look at this tag generation procedure with a specific source. So, let me assume that I have a source S consisting of 3 symbols with the probability model given as probability of S1 is equal to 0.80, probability of S2 is equal to 0.02, and finally probability of S3 is equal to 0.18. Now we would like to encode the sequence 1, 3, 2, 1. Right? So indirectly we are encoding the sequence S1, S3, S2, S1 because we are using the mapping x of Si is equal to I. So from this probability model we can calculate the cumulative distribution function as follows. This is equal to 0 for k less than equal to 0. Fx1 is equal to 0.8, Fx2 is equal to 0.82, and finally Fx3 is equal to 1.0. So the first symbol in the sequence is 1. So let us generate the upper limits and the lower limit for the sequence at this stage. We will initialize L0 equal to 0 and U0 equal to 1. So L1 will be given by this relationship which we have derived earlier, L0 plus differences and Fx of xn minus 1. In this case your xn is 1. Therefore 1 minus 0 is 0. So I require the cumulative distribution function for 0. So if I substitute these values out here, I get L1 is equal to 0. Similarly for U1 I can substitute the values I get here. This is of f of x xn. Xn in this case x1, that is 1. Therefore I write Fx1. So if I substitute these values I get U1 equal to 0.8. Now so the tag for the sequence after observing 1 is contained in the interval between 0 and 0.8. The second element in the sequence is 3. So L2 and U2 will be given as follows. L2 is equal to L1 plus U1 minus L1 and Fx of xn minus 1. Xn in this case is 3. So 3 minus 1 is 2. Therefore we get Fx2. If you substitute the values you get 0.656, and similarly U2 will be given as shown here. In this case xn is 3, so I write the cumulative distribution function for 3, I get 0.8. So at the end of observing 1 and 3, the tag for the sequence 1, 3 is contained in 0.65 to 0.8. So if you progress in this manner, the third symbol is 2, and this results in the following update equation. You get L3, this is your L2, this is your U2, and similarly U3 is given by this. So therefore a tag lies in the interval given by this. And finally we have the fourth element, that is 1, and if we take that into consideration, finally we get the upper limits and the lower limits as shown here. So the lower limit is given by 0.7712 and the upper limit is given by 0.773504. It's important to note again here, this becomes fx0 because this is 1, xn is equal to 1, that is x4 is equal to 1. Therefore, you get this limit L4 as the same as L3. So, the tag for the final sequence 1, 3, 2, 1 can be generated as the midpoint of L4 and U4, that is 0.772352. Now, from this we observe that each succeeding interval is contained in the preceding interval. Now, this property we will use to decipher the tag. The only undesirable consequence of this process is that the intervals get smaller and require higher precision as the sequence get longer. So, in order to overcome this difficulty in a practical scenario, a rescaling strategy is adopted. So, we have looked at the procedure for generation of the tag. Now, let us look at the procedure to decipher the tag, that is decode the tag. Now, we have seen that a sequence can be assigned a unique tag given a minimal amount of information. Now, deciphering or decoding the tag is as simple as generating it. We will study this through an example. So, let us consider tag obtained in the previous example, which we used to explain the generation of the tag. So, the tag value which we generated was given by 0.772352. The interval containing this tag value is a subset of every interval obtained in the encoding procedure. Now, our decoding strategy will be to decode the elements in the sequence in such a way that the upper and the lower limits will always contain the tag value for each k. So, we will start with L0 equal to 0 and U0 equal to 1. After decoding the first element of the sequence x1, the upper and the lower limits become L1 is equal to 0 plus 1 minus 0, x1 minus 1, that is equal to f of x1 minus 1, and the upper limit after decoding of the first element will be fx x1. So, in other words, the interval containing the tag is, after decoding of the first element, will be given by this interval. So, we need to find the value of x1 for which 0.772352 lies in the interval, correct. So, now if we pick, so if the pick is x1 is equal to 1, the interval turns out to be 0.0 to 0.8, and if we assume x1 is equal to 2, the interval is as shown here, and finally for x1 equal to 3, the interval is 0.82 to 1.0. Now, we want that our tag 0.772352 should lie in the interval, one of this interval, and from here it is very obvious that this lies in this interval. Therefore, for the first element x1 we pick up as 1. Now, we repeat this procedure for the second element in the sequence, that is, let us call it as x2. So, now the upper limit and the lower limits will change as L2 is equal to, because the lower limit is 0 and the upper limit is 0.8, I calculate this, I get this value, and similarly for the upper limit I get this value. Now, again I have to choose my values of x2 in such a way that my tag lies in that appropriate interval. Now, if I choose my x2 equal to 1, I get this interval. If I choose x2 is equal to 2, I get this interval, and if I choose my x2 equal to 3, I get this interval. These intervals are obtained by substituting the values for x2 in this equations. Now, if I choose my x2 equal to 3, then I get this interval and my tag lies in this interval. So, I choose my x2 equal to 3. So, knowing now x2, I can update my L2 and U2 as follows. So, my L3 and U3 will be as 0.65, this should be L3 and U3 as given by this expressions. Now, again I have to choose that value of x3 for which my original tag of 0.772352 lies in this. Now, if you look at this expression, these are a little bit cumbersome. So, so if you want to simplify the comparison, we can subtract L2 from both the limits. I subtract 0.65 from both the limits, and then you find x3 for which then it contains 0.772352 minus 6.5, because I subtract this from my tag also. So, I have to find out x3 such that this value lies in that interval. Now, again if you look at this, this comparison also is a little bit cumbersome. So, the comparisons can be further simplified by dividing the residual tag of 0.116352 by 0.1444. So, if I do that, if I divide this number by 0.144, I get 0.808. So, comparisons further simplified by dividing the residual tag of 0.116352 by 0.144 to get finally 0.808. And finally, find the value of x3 for which 0.808 falls in the interval given by this. Again, if you substitute x3 equal to 2, this satisfies the requirement. And finally, I get my L4 and U4 given by this expression. Now, again I have to find out x4 such that it lies in this interval. Again I can subtract out this L3s from both the thing and then divide by 0.00288. So, if I do this, what I get finally is this. So, I subtract L3 from the tag to get this. I also subtract it from my L4 and U4, and then find the x4 for which the interval is this. Further simplification is by dividing 0.001152 by 0.00288. So, I get 0.4. So, I have to find out x3 for which 0.4 is contained in this, and if you do that, you find x4 is equal to 1. So, in short, we can summarize the algorithm to decipher the tag as follows. So, algorithm to decipher the tag is as follows. First, initialize L0 equal to 0 and U0 equal to 1. For each k, find the modified tag value as t minus L k minus 1 then find the value of xk for which fx xk minus 1 is less than equal to modified tag value, and after having done this, update UK and LK. So, continue until the entire sequence has been decoded. So, now we have seen the procedure for the generation of the tag and also how to decipher the tag. The next logical step is basically to represent this tag by binary representation if we are using the binary alphabet. Now, in the next class, we will look at the binary representation of the tag that forms a unique binary code for the sequence. We will also look at the uniqueness and efficiency of the arithmetic code.